In this video, we'll prove a lemma which we'll use in various contexts about the number of roots of a given polynomial of bounded degree. So let's state this lemma. So this lemma can be attributed to Lipton, DeMillo, Schwarz, and Zippel. Schwarz and Zippel proved the same result independently a bit later than Lipton and DeMillo. And in the literature, this lemma is usually called the Schwarz-Zippel lemma. So let P be a polynomial of n variables with coefficients taken of some field f. For now, for intuition, you can treat it as a polynomial with, say, real coefficients or rational coefficients, or coefficients being residues over some prime p. It doesn't matter. So currently, you can treat this as a polynomial with real valued coefficients. And now, let S1 through Sn be subsets of this field f. So now the lemma gives an estimate for the number of ways to choose the values of each of the variable from the corresponding subset, so that the given tuple of values is a root of this polynomial. So we'll assume that all these sets Si have cardinality at most m, and the bound which is given by this lemma for the number of ways to choose a tuple S1 through Sn such that S1 belongs to the set capital S1, Sn belongs to the set capital Sn, such that P vanishes on this tuple of values, the number of these tuples does not exceed the degree of the polynomial multiplied by m to the power of n minus 1. We can treat this as a generalization of a theorem on the number of roots of a polynomial over a field. So if P is a polynomial of a single variable x, which is not identical 0, then the number of roots of this polynomial does not exceed the degree of this polynomial. And this is a special case of this statement, because here we have n equal to 1, the number of variables, so here we would have just 1, and this all gets down to the statement that the number of roots of a polynomial does not exceed its degree. But we'll actually use this theorem of algebra as a base case for our induction while proving this lemma. So we'll assume this as a known fact for a polynomial of a single variable, and now we'll prove the lemma by induction on the pair of values, induction on both degree of the polynomial and the number of variables. So what does it mean to carry out the induction on the pair of values? So usually, when we have just one parameter of the induction, this parameter is oftentimes just a natural number. We prove our statement for the smallest number, then we prove that we can translate it into a larger one, and thus we can cover all the positive integers, proving that each of them satisfies our statement. Or to put it the other way around, if we are to prove our theorem for the larger integer, we can rely on the smaller one. To prove it, we can rely on the smaller one, on the smaller one, on the smaller one, before we come to the base case, which we also prove separately, and thus we know that our proposition holds for all the positive integers. So now the picture for the induction carried out for a pair of parameters would look approximately like this. So if we plot this space of our parameters, so here we say have degree of the polynomial growing, here we have the number of variables growing. Our base case would be when n is equal to 1 or when d is equal to 1. So we essentially have all these points covered by the base case when n is equal to 1, and all these points covered by the base case when degree of the polynomial is equal to 1. And then, taking some pair of a polynomial of some degree and some number of variables, we'll prove the validity of our proposition for this pair by relying on the validity of the same proposition for some pairs which have at least one of the parameters smaller. So to prove the proposition for some point of parameters, we rely on pairs of parameters that are standing to the bottom and to the left of this point. So thus, eventually, we get to one of our base cases. So thus, our proposition is true for all the possible combinations of parameters. So let's now prove the induction base. So the base case, when n is equal to 1, is just a standard theorem of algebra. That's a polynomial of a single variable has no more roots than the degree of this polynomial. Now, the second type of base case is when the degree of the polynomial is equal to 1. Here we have a polynomial p of x1 up to xn being just a linear combination of the variables. Without loss of generality, we can assume that, say, the coefficient c1 is non-zero, and let's now estimate the number of tuples on which the polynomial p vanishes. So for such tuples, x1 should be 1 over c1 of minus c2 x2 minus cn xn. So now whatever values we choose for x2 through xn, for every such choice, this thing takes some value, and there's only one choice for the variable x1, so that this equality could hold. So if we have cardinality of S2 choices for x2 up to cardinality Sn choices for xn, the number of choices for all the values of x's is the product of the cardinalities. Now every such choice leads to some specific value here, and so there is just a single x1, well, actually at most one x1, because x1 should be an element of S1. So if S1 does not contain an element which exactly equals to this thing, then we have actually 0 choices for x1. But anyway, even if S1 contains such a value, then there is at most one choice for x1. And so the number of tuples does not exceed just the product of cardinalities from S2 to Sn, which perfectly corresponds to what we are proving. Degree of p is in this case 1, and the product of the cardinalities of S2 through Sn does not exceed m to the power of n minus 1. Let's now proceed with the induction step of our proof. So let's assume that variable x1, without loss of generality, enters our polynomial with degree at least 1, so it actually is included in our polynomial. And let's write our polynomial over various degrees of the variable x1. So that is, we'll group all the monomials that contain only variables x2 and xn, not containing x1, and we'll group these together and we'll name this the polynomial p0 of x2 through xn. Then we'll take all the remaining monomials that have variable x1 in exactly first degree in them, and we'll take x1 away from them, and they together without x1 will be named by p1 of x2 through xn, and so on and so forth. So the last portion of monomials, they contain x1 to some degree k, and we take x1 out of them, and they will be grouped together and called a polynomial pk that just contains variable x2 through xn. So now let's estimate the number of tuples s1 through sn such that p vanishes on these tuples. Now these tuples can be of two kinds. The first kind of the tuples on which pk vanishes, so that pk of s2 through Sn is equal to 0. And the second kind are the tuples on which pk doesn't vanish. So let's now first bound the number of these guys such that the subtuple S2 through Sn makes pk vanish. Now, the degree of the polynomial pk does not exceed the degree of polynomial p minus k, because whatever monomial we take out of pk, when we multiply it by x1 to the power of k, this monomial will not vanish when we add it with other monomials from here, because it has the highest possible degree of x1, and thus it will eventually enter the polynomial p, and when we take product of two polynomials, the degree of the product is equal to the sum of the degree of the individual components, and thus we cannot have monomials of degree higher than this one in pk. So thus we can apply induction hypothesis to polynomial pk and say that if pk vanishes, then the number of ways to choose S2 through Sn does not exceed, by induction hypothesis, the degree of the polynomial, which does not exceed itself, deg p minus k, times m to the power 1 less than the number of components here, so that's n minus 2 we have here. And each of these tuples can be augmented to a complete tuple from S1 through Sn in at most m ways, because there are at most m ways to choose the variable x1. So now let's bound the number of these tuples. The number of ways to choose S2 through Sn does not exceed m to the power of n minus 1. But then for each fixed choice of S2 through Sn, for which pk does not vanish, our polynomial p turns into a polynomial of a single variable x1, a polynomial of degree k. And now the number of roots a polynomial of degree k of a single variable can have is at most k. So there are at most k ways to augment our tuple to form a tuple of values s1 through Sn. And now adding these two things up gives us exactly the thing that we are looking for. So this completes the induction step, and thus it completes the proof of the lemma. And the lemma that we have just proved has a very nice probabilistic interpretation. So if we use a corollary of this lemma, which is when all the cardinalities of our sets are exactly equal to m, we can state this lemma in terms of probability. So suppose that we have our polynomial p of x1 through xn, and we are choosing the values for all the variables, each value from its own set, independently at random. Usually there's a notation for a random choice like this. So each variable si is chosen independently of the other variables at random, uniformly from its own set si. So then, what would be the probability that this tuple of values makes our polynomial vanish? So when we plug s1 through Sn into our polynomial, the probability that p will vanish on this tuple of values can be bounded by the number of the tuples on which our polynomial vanish. So that's this one according to our standard formulation of the Lipton, DeMillo, Schwarz, Zippel lemma, divided by the number of all the tuples. And when all the cardinalities are equal to m, the number of all tuples is just m to the power of n, so that simplifies to just degree of p over m. And this is actually the variant of the Schwarz-Zippel lemma that we'll use later on for designing probabilistic algorithms.